So today's topic is about functions of several variables, but we have to begin with the functions with two variables, right? Functions with two variables. Function of two variables. Now, how to define a function of two variables? Well, we have to understand the function with one variable, right? The function with one variable, not everybody fully understand a function. A function, okay, in general, okay, a function is just a rule that assigns to each point in the so-called domain a unique point in its range. So here's a set, okay? This is a set. This is called the domain. Now this one could be a set in two-dimensional space, could be an interval in one-dimensional coordinate line. Okay, then this is another space. Okay, this is called the range. Okay, so right now I draw it like a two-dimensional set. So this is a F. Okay, okay, and here's a point P, and this is a point Q. Okay, so you find, yeah, we assign this is a function is a F is a rule. Okay, this is the very most general definition. Okay, that assigns to each element or point, or sometimes we call it element, in a set domain called D, and that's called range. In a set D, unique point or element in you get set A. Okay, so that's it. So that's a definition. F is just a name. Okay, a function. F, yeah, and its name called F. You know, you can use any letters. That could be you can use a combination of three letters. Okay, so if you already know programming, you know that you can use 5 letters and 1 letter, okay, F. A combination, just like a password. Okay, you can have 1 letter, 3 letters with the numbers. Doesn't matter. Okay, just a name of it. Okay, and so you can also write Q equals F of P. Okay, so this is a given a point P, then you get another point Q in the set R. Okay, so this is called a function. Okay, now if I if there is a range I is in the one-dimensional coordinate line, and D is in the one-dimensional coordinate line, then this is the usual function we already studied in calculus 2, calculus 1 and calculus 2. Now this course is called calculus 3. Okay, and today we're going to look at a case. Yeah, if I look at a case when D, yeah. So this is the first case. Yeah. So D is a domain, is a set, right? Is a set in R2. Okay, and R is a set in R1. Okay, so now this is you have a set. Okay, and here it is just 1. coordinate line. Okay, so you will get, let's call, yeah. So every point here, P has two coordinates. Okay, has two coordinates. For the x coordinate, y coordinate, this is sent to here, and by the F, and the image is, yeah, this is a D, this is my R. Okay. But you have to give me the formula to do that, right? So the variable here is called the Z. Yeah, and let's call the Z-axis, okay? Then this is a point, that Q actually is a point Q. Q has coordinates, yeah, only one number for the coordinate, right? It's called Z. So we can find out a formula sometimes, yeah. So how do you describe this rule, right? That you have to give me the, sometimes there are many ways to describe it. Sometimes you can give me a graph. Sometimes you can give me the, yeah, usually defined by a formula, okay? F is usually described by a formula, okay, by a mathematical expression, okay, or mathematical expression. So this is a f of x and y, okay. In terms, for example, like x squared plus y squared, okay, such as this, okay. So once you give me the value, give me the coordinates of the point in the domain, I can calculate and the value by using this expression, x squared plus y squared, right? So assign to each point in the domain a unique number, okay? How do you get that unique number? Using this expression, the given expression, okay? And yeah, you can also figure out the specific value at a specific point. You can figure out the value at a specific point. For example, when when f like a 1 and a 3 and a 4, right? Then you get 3 squared plus 4 squared, and you get 5 squared, which is 25, okay? And then we say 5 squared is the value of the function in this case. Yeah, it's a number, that's what we call value, okay? It's a valid function at the point was coordinates 3 and 4. So 5 squared is the value of f at the point 3 and 4. Okay. Okay, this is part. So let's take a look at some examples. Okay. For given f, okay. So given f, so when we say given function f, that means we're given the expression. Okay. So f is going to be square root of x plus y. I just use this, and x minus 1, for example. Okay. Let's study this. Okay. Find or evaluate the function as the value of the function at 1 and 2. Okay. Then and the domain. Now, what's the definition of domain of the function? If the domain is not given, so that means it is a set on which the function is defined. Okay, so this is a set in R2. Okay, the set of points R2. Yes, a set of points at which the function, the expression, the formula is defined. Okay. Okay. Okay, that's a definition. Okay. Unless I give another restriction on the points. Okay. All right. So let's take a look at F1, 2. x should be 2, right? So it's going to be 1 plus 2, and the 1, it's not defined, right? So clearly it says that it's undefined. So this is a no value, f is not defined at this particular point, okay? So there's then there is a then you come to the next problem. Say, so for what kind of point the function is defined, right? At what kind of point the function is defined. You look at this, right? So f of x is defined if and only if, okay? First of all, square root of x plus y should be defined. So x plus y should be greater than or equal to 0. Another condition is this cannot be 0 in the denominator. If the square root, if the numerator is not defined, then if the numerator is not defined, then the function is not defined, right? Right. So how can I draw the region described by the first inequality? Well, you have to look at what is x plus y equals 0. X plus y equals 0 is this line. Okay. Now, which side is x plus y greater than or equal to 0? I'm pretty sure this side. Okay. This side. Right? Yeah. This side, x plus y is going to be greater than or equal to 0 because you can pick up a point on this side and plug into the inequality. So this side, x plus y is greater than or equal to 0, including this strict line. Now, x is not equal to 1. X equals 1 is this vertical line, right? That's the x equals 1. And this line should be excluded, right? This should be, excluded. Okay, so that means you're going to have two regions in this case, like a separate, right? So one region is here on the left side of this line, other region is on the right hand side of this line. Okay, so this is a domain. So domain consists of f consists of two regions, okay? Two regions that disconnect. It's not a one piece. Okay, so so the point 1 and 2, where's the 1 and 2? The point 1 and 2 is here. And this point is on the line. It's not in the domain, that's why I undefined. Okay, this is a 1 and 2. Let's find another problem from the exercise. Okay. Okay, let's look at the next problem. So f of x is going to be 1 plus square root of 4 minus y squared. Okay. We want to find out the value of the function and evaluate f 3 and 1. Okay. And so we have to find out the range, find the domain, and the range of the function. Okay. Yeah, the range is a little bit difficult to find. The domain, I think it's easy to find. Okay, so first of all, you evaluate this, right? When x equals 3, y equals 1, so it's 4 minus 1 squared. And that is going to be 1 plus square root 3. Okay, I cannot simplify it further. It has a value. So that means the point with coordinates 3 and 1 is in the domain. So how to define the domain? Domain D is going to be the point such that this expression should be defined. And this expression defined if and only if this will be 4 minus y squared is greater than or equal to 0. So let's solve this inequality. Okay, 4 minus y squared greater than or equal to 0. So y squared is less than or equal to 4, right? Then the y is going to be very careful. Solving this inequality is absolute value y should be less than or equal to. How to do that? Yeah, because this is it's not like a y less than or equal to.
Why did you
Y
switch
could be
the sign between the y squared and 4? Why did you flip the sign?
oh, well, I can write the y minus y greater than 4 is greater than or equal to y squared, but traditionally the notation will be the variable is on the left, the number is on the right. Okay, that's why I switch it. These two are equivalent. Okay. Yeah. So you can say x4 is greater than or equal to y squared, but that's the same as y squared is less than or equal to 4. So we usually put the variables on the left, the numbers on the right. That's a traditional way to express an inequality. Okay. All right. So now we get a domain. Okay. So you have to draw the picture because otherwise you still only simplify it in this form. Okay. So let's sketch the graph. Let's sketch the graph. Yeah, save space, I put it here. So how do I sketch the graph? You see, the absolute y is less than or equal to 2. So you just look at the two extreme case, the absolute value y equals 2. So one is this line, so y equals 2. Another line, y equals -2. Okay, so any number between those two, any points between those two horizontal lines satisfy this condition. Okay, so this is a domain of the function. The function is defined on this region between those two parallel lines, horizontal parallel lines. Okay, so this is a domain. The function is not defined somewhere else, just outside. It's not defined, including these two horizontal lines. Okay. Now the difficult part is to understand the range. Okay, look at this function. Okay, look at this function. Okay. First of all, the second term is never be negative, right? So it is always equal to 1 and plus 0. And this can be 0, right? It can be 0, it can be 1, yeah, plus 0 when 4 minus y squared equals 0. So the value of 1 can be reached. Right? So the value of 1 can be reached. But can the value of the function arbitrarily large? I think so. Maybe not. Okay. No, I did not say so. I did not say that. Okay. So let's look at the possible value for square root of 4 minus y squared. Okay. I think 4 minus y squared, right, is always less than or equal to 4, right? So that means f of x, y for the function for the points in the domain is less than 1 plus square 4, which is 1 plus 2, which is 3. So you get the upper bound, you get lower bound, right? And it's obvious the function can take any value between 1 and 4. So I think the range, the range of the function is going to be the y is going to be is going to be the interval. I just write on the interval, okay? From 1 to 3. Okay. So that's a range. Okay. So this function maps the whole region onto this line, onto this region, okay? Yeah, so this is a range, this is a domain, this is a range, okay, of the function. Yeah, right, there's a restriction here. You know, the value of the function cannot be arbitrary, because inside radical is a 4 minus y squared. Then 4 minus y squared cannot be too large. Otherwise, yeah, it's always less than or equal to 4. But also cannot be negative. So it's between 0 and 4. Okay. Then the value function is between 1 and 3. So that's it. It's good. It's a good problem. Now we can, yeah, then we should talk about the functions which cannot be defined by a mathematical expression. Okay, sometimes can be only defined using a table of data. Okay, so in that case, and yeah, we can define, yeah, f is defined. Yeah, let me find a good example for this. Yeah. F is defined by just the table data. Okay, so how can I describe it? I just make a very simple example. Okay, and here's a from the points of domain, right? So I get and here's x and a y. It's the x and y, but they take a and this is a z. Okay, so here's a 0 and the 0, and you get 1, and the 1 and the 0 you get 2, for example, right? 0 and the 1 you get -1, and the 1 and the 1 you get 0. Okay. So what does that mean? So that means to each of these 4 points, I assign a unique value to the function. Okay. So the domain in this case consists of 4 points. Okay. And the range also consists of those 4 numbers. So I can write express in this form for -1, 0, 1, and 2. And we in this order. Order doesn't matter. Okay. So the function is not defined for any points which are not in the domain. Okay. And if asking me what is the value of 0, 1, I just look at this table, and this is going to be -1. Okay. So that we're not going to spend too much time on this type of functions. This is called discrete function. Right? They're not going to, well, we cannot use a calculus derivative to study them. That's why we don't want to spend too much time on that. Okay. Okay. Most of the time, we are given a formula for the function. Okay. So let's take a look at another problem before we study the graphs of the function. Okay. So let's take a look at problem number. Yeah, given the function here, f(x,y), and the fourth root x minus y. Okay, so we want to find the domain of the function. Okay, okay. Find the domain. Now if possible, and the range. Okay. So this is a force root. Force root like a square root. Okay. And this is defined only for a greater than or equal to 0. Okay, that because the force root. Okay. Yeah, it's force root of A. So in order to find the domain, you just needed to solve this inequality. Okay. Right? And this inequality, how can I describe this inequality? Well, this inequality, you just need to describe it as equality first. Okay, that's how they draw it. Okay. So x minus y equals 0. Let's look at this. So y is going to be 1/3 of x. So this is a line passing through the origin and has a slope of 1/3. So this line. Okay, this line should be in the domain. But which side of the plane is the domain? You have to test it. You have to check because this expression x minus 3y does not change sign in any of these domains. So if at one point it's always positive, then every point in this on the same side will be positive. So let's take a look at this point when it's 0. Okay, at that point, f type 1 and 0 is going to be 1 minus 3 times 0. So it's 1, it's positive. So that means, not f, okay, I shouldn't say f. So this is different from my function. I don't use the same notation. Okay, just plug them into the expression, okay, into the expression. So that means on this side, x minus 3y is greater than 0. On this side, x minus 3y is always less than 0. This side is greater than 0. Okay, so including the line. Okay, now I can describe the region. Okay, so this is a region satisfied by this inequality. Right, so this is a domain. The question is, what is the range? Okay, what is the range? As you can see that the force root of x minus 3y this never be negative. Okay, but it could be 0, right? When it's 0, when x minus 3y is 0. So the value could be 0, but it's always, in general, it's greater than or equal to 0. Now, does it have an upper bound? I don't think so. Okay, so this can be as large as possible. Okay, so so the force root x minus y can go to positive infinity as x minus y approaches positive infinity. Okay, that's possible, right? You let y to be 0, let x go to infinity. So that means, so the range is going to be the interval from 0 to infinity. Okay. Okay. So if we want to draw the picture for this is the interval. Let me mark it. Okay. So the function is send the whole region onto this interval from 0 to infinity. Okay. Yes. Now, if here's the definition. Okay, f is called a linear function if the formula for the function is going to be in this simple form, no square. Okay, that's a very special function. For a linear function, you will see that the domain is going to be the whole plane because it's defined for any x, y. Okay, so the domain is going to be the whole, okay, the whole plane. Okay, now what is the range? We have to be very careful. The range, if a and b are not all equal to 0, the range is going to be the whole line. Okay, this otherwise just a point. So this is in the case a and b are not all equal to 0. Okay, one of them 0 is okay. Okay. Otherwise, it's not a linear function; it's become constant function, right? So this is a linear function, is very special. All right. So I'm going to talk about the graph. The graph of a function f. Okay. Well, this is going to be the set in R3. Okay, defined by is set determined by the coordinates x, y, z, defined by x, y, z, where x, y are in the domain D, okay, and z is always given by this formula. Okay, so that means, let me draw the picture. Okay, here, first of all, you have this map, right? So this is z-axis, and the function is defined on this domain, right? It's x-axis, y-axis, and then you get the range. This is R, this is D. Okay, but it's harder to view details. If you draw this is origin definition. What I'm going to do is I move the z-axis and put it into space. Okay, so now it's harder to draw it because it's our screen is two-dimensional. Okay. 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 By the way, why you have to take like 171 first, math 172, in order to take this course? Because we are not going to go through all these pictures, 3D, 2D. I just show you how to draw quickly. Okay, so this is axis, this is y-axis. Okay, and I put a z perpendicular to xy plane. I go to space. So my domain right now is D in the xy plane. Okay, so this is the only way I can draw like that. Okay, so for every point, right, and you get another, to each point in the domain, you assign a unique value, z, right? Z equals f of xy. So for any point here, okay, what I'm going to do is I draw the point, plot the point here in the space, and this, if here's x and y, then get an x and y, but the z is determined by the value of f of x. So the point can be very high, can be very low. It depends on value of the function. So when you move all the points over to this domain, what I got is kind of a loose, yeah. It's harder to draw it. It looks like that. Okay. So this set is usually a surface in the three-dimensional space, and that is called the graph of the function. Okay. Yeah. This is called a graph of function. So this is a graph of f. Okay, and so you can visualize it. Okay, the graph gives you more visible data about this function. Okay, you can say where the graph, where the highest point, where the lowest point. That the highest point corresponds to the maximum value of the function. Okay, right? And the lowest point on the graph corresponds to the minimum value of the function. But so let's take a look at some examples. Given a linear function, okay, and that is going to be that's going to be, let me think about that, x plus 3. Okay. So, well, you see, it's only one variable, that's fine. Just independent of the y variable. Okay. So this is the function, okay, and can we sketch the graph for the for the graph? Sketch the graph of f in three-dimensional space. Now this becomes challenging because not everybody really able to familiar with the 3D pictures, how to draw it. Okay, so the graph, okay, of f, okay, the graph of f consists of those 3 points, and where no restriction on x and y. So where z is going to be x plus 3. Okay, so z is x plus 3. So there's a relationship between z and x, but no restriction on the y value. I think it's easy to draw it because this is the x. Now, if you just in the x, y, z plane, z equals x plus 3 is going to be a strict line, and this is 3, and this is like that. This is a line, okay? But how can I draw it here? I think it's passing through the point 3, and yeah, it goes like this. Yeah, let me draw the line using red color. All right, so this is on the x z plane. This point is on the xz plane. But there's no restriction on the y variable, right? So that means, yeah, this is it's a little bit challenging to draw. Okay, so I'm going to draw this line like this. I draw the horizontal line parallel to this, okay? And maybe that helps. Okay. So there's this should be the plane, okay? Plane perpendicular to the xz plane, and determined by this line, as this line in red color, right? So now I'm going to color it. Okay, so this is a graph in the, yeah, if I want to extend it, then I just draw one piece of the graph, okay? Yeah, just draw one piece of the graph. And actually you can extend it. Yeah, extend it. That's this plane, the graph is a plane. Let me describe it, okay? The graph is a plane perpendicular to the xz plane, okay? Okay. And it intersects the xz plane on along the line, okay? Along the line z equals x plus 3, okay? In the xz plane. So imagine you can draw the line in the xz plane using the equation, then draw another plane perpendicular. Okay, I'm going to ask you to do the next one. Okay, given xy is going to be 9 minus x squared minus y squared. Okay, first find the domain. Then sketch the graph of f in three-dimensional space. Okay, please try that first. All right, I hope you figured out how does it look like, okay? So first of all, you will see that you just solve this inequality, okay? This cannot be negative, okay? And then x squared plus y squared should be less than equal to 9. And how can you describe this, right? So it's going to be x squared plus y squared equals 9 is going to be a circle with radius 3, right? So this circle with radius 3. Okay, so including this, so that is a domain. That is a domain. So this is a domain. Let me just switch. Okay. So you get a domain. Now you can also try to find the range because 9 minus x squared, this is also less than equal to 9. So the value of the function is less than equal to square root 9, which is 3. So that is so the domain is a circle, and the range is just going to be 0 and 3. Okay. All right. How do we sketch the graph? Well, you can somebody. Oh, never mind. Okay, it's hemisphere. So you look at the equation. Okay, look at this equation. So z is going to be square root of 9 minus x squared minus y squared. So you modify this equation, but z is greater than or equal to 0 anyway, right? When you modify You get z squared equals 9 minus square minus 1 square. And I can move x squared, y squared to the left. I get a 9. So 9 is 3 squared. So it is a sphere with radius 3. But on the other hand, z cannot be negative. Okay, so it is a hemisphere. It is the up hemisphere, okay, in the space. Okay, so this is a circle, and this is the one, and have absence. Okay, so this is how does it look. Okay, you see, you have to make it looks like a 3D graph. Okay, it's a yeah. Right. You don't need to be very, I'm being like an artist. Okay, so I think if you let the kids to learn how to draw some 3D objects when they're in the elementary school, they get the benefits of that. They can do better drawing than other people without this additional tutoring in the school. Okay. Our next problem is going to be, well, before talking about, I don't have much time left, so I'm going to talk about so-called lever curve. Okay. The lever curve. The lever curves. Okay. The lever curves are function f, okay, of two variables. And more variables can be defined the same way. Okay, of two variables. Right, those are going to be the curve determined by the equation. Okay. In its domain. Okay. Described by the equation of this. Okay, k is a constant. Why we want to study lever curves? For example, a typical example is if you want to describe the mountain, the function actually gives you the height of the function gives you the height of the mountain at a particular point. Then the lever curve is actually tells you, if you only have 2D picture, right? How do you do that? So this is a graph. Let's visualize it. This is a domain, and this is a graph. Okay. Okay. So now this is the domain. This is y-axis, this axis. Okay. For if f xy equals k, so along this you use a line, use a plane perpendicular to that. This is a z equals k. So the intersection, okay, is a curve on the surface, on the graph. But if you project it to the domain, so this is the lever curve, okay, of f of x, y equals k. Because along this curve, the value of the function is always equal to k. So here, the value of the function x, y, the third value is k. Okay, it's a fixed. Can you see that, right? Okay, so that is a lever curve. So when you look at the map, right, you want to go hiking. Okay, the map is not 3D map. Otherwise, you don't need it. On computer, maybe you can do that, right? But it's just on a piece of paper. The only map I can give to you is a two-dimensional plane, okay? So this is the domain. So here is a level curve. So along this curve, I can tell you the height of the mountain, okay? So here x, y is going to be k. So k is a value like, 3,000 feet or 2,000 feet, okay? So you can see that if you go into the middle, the value of the k increases, okay? So maybe it's sometimes the opposite way, because if this is it's with a valley of the, surrounded by the mountains, right? Then k value can go down. So you can tell that from the two-dimensional map, you can tell that how high of the point of that this particular, how high of the point, right? So that's why in order to understand the three-dimensional object, you can use a two-dimensional map, right? And with the level curves indicate level curve. Okay, now let's take a look at this examples. Okay. Sketch the level curves of the function fxy equals y minus x squared. Okay. So right now we are in two-dimensional. Okay. So in two-dimensional, the function is defined. So what we have to do is we have to study this family of equations. Okay. So y minus x squared equals k. So in other words, y equals x squared plus k. So k, the value of k changes, you can get different level curves. So this is the xy plane. The domain of the function is the whole I, okay? The domain of the function of f is the whole plane, okay? Clear. So when k equals 0, you get a parabola. It's this is a k equals 0, right? When k equals 0, this is a curve corresponding to k equals 0. So when k equals 1, you just shift the parabola upward by 1 unit. Okay, k equals 2, and you can move down, right? K equals -1. So you get a bunch of the curves, okay, and tells, and for different values k, okay, for different values k. So that is called the level curves of the function. And here's another example. Sketch the level curve of the function f, okay, which is given by x squared plus y squared. Okay. It could be a square root of x squared, it's x squared plus y squared. But so you have to draw the graph. You have to draw a family of curves in the xy plane. Okay, so you will get. Think about it. I'll give you. Let's try it. Give you half a minute. Okay, think about how to do it, how to figure it out. Right, so let's sketch the graph. Right, so we can look at this family of equations. Okay, now clearly k cannot be negative, right? K cannot be negative. So so first of all, you see that k cannot be negative. Okay, then x squared plus y squared is going to be like a square of k and square. So this describes a circle. The general picture circle was a radius k. Okay, so this is when f x y equals k, that means it is a circle with radius, yeah, radius square of k. So that's clear enough. Okay, if you want to draw different curves, then you can say k equals 0. Here's a point. K equals 1, right? And the k equals 4. So that's a 4. That's k equals 1. Because when k equals 4, the square root of 4 is 2. The radius is going to be 2, right? So it just double the radius. Right? Three curves is enough. The first curve is actually the point. Right? Yeah. But if you want to draw the graph, how does it look like? So graph. And here's a picture. Z equals xy plus y squared. Right? This is going to be parabolic. Okay, so if you're coming down to here, you get a circle. Okay, so this is a point, it's a 4. So here's a k equals, yeah, when k equals 4, right? The radius is going to be 2. Okay, so this is this is a typical example. And here another circle, then you get a unit circle. And this is a 1 when k equals 1. Can you see that, right? I think that's so the level curves is just the projection of the graph at a certain level. Okay, it depends on the value of f along. Okay, so that's what called a level curve. Right? It tells you how high of the graph at that particular point. Okay, well, the curves actually gives us the projection of the curve in the graph with the same height. Okay. So it's a graph and the level curve. Now, the function, okay, you can have a more than one variable. Okay, you can have a 3 variables. Can have let me talk about a few examples of a 3 or more variables. Okay, functions of 3 or more variables. Well, there are some quantity. It depends on not on just one variable. It depends on 3 variables. For example, if you want to describe the temperature in the space, so at every point in the space, it's a 3-dimensional space, you get a value, right? Assigned to each point in the space a unique value, which is called temperature. So the temperature function is a function of 3 variables, right? Clear? Okay. So the function could have 3 variables. The function can be x, y, z, w, have 4 variables, and so on. This can be understood in a similar way. And then you can talk about graph. It's harder to draw the graph. If it's a function of 3 variables, how can I draw the graph? You have to go to 4-dimensional space, right, to draw the graph. If a function of 4 variables, you have to draw the graph of this function will be in high 5-dimensional space. We cannot, it's almost impossible to do that, right? Because of the limitation of the space we live. Okay? And most of the time it will be out of your imagination. Okay, so but we can look at this one example, and I hope you can, yeah, we can understand the function of three variables using the so-called level curves, level surfaces in this case. Okay, so take a look at the example. Okay, so given a function x, y, z, okay, and that is going to be yeah, it's going to be say x squared plus y squared plus z squared type of this. All right. So we're trying to see. Okay. So the domain is going to be no restriction x, y, z. Okay. So that's just a whole plane, the whole space. Okay. However, the range of this function is going to be the set from 0 to infinity because this never be negative. So now the domains are, this is a domain, okay, not the three-dimensional space, so just domain. So the function defined on whole space. You can view it as a temperature function, for example, at the origin of the space, the temperature 0, right? And it's getting higher and higher the temperature when the point is going away from. But if you look at this, this equation, this determines so-called level surface, okay? Because it describes a surface. We don't call it level curve. Okay, then what? Right. Then you look at this equation. Right. So this can be viewed as square root k squared. K cannot be negative, right? So you can actually, this is a sphere. Okay. So around this, over the sphere, the value function has a constant value. Okay, it's constant. So you can have another sphere around that. It's harder to draw it, okay? And let's just draw two level surface. Yeah. Okay. They just draw the two level surface. Okay. And as k increases, the level surface, as a sphere expand. Okay. So this is how do we understand. We cannot draw the graph for this function with three variables, but through the level surfaces, we can still understand the function, the behavior of the function. Okay? Because along these level surfaces, okay, I know that have a constant value of function. Okay. Okay. Right. So this is how do we understand the function. So if you get a 3D picture about the function of a three variable, you don't see the graph, but you still can tell, okay, the temperature of the function, okay, at each point, okay, with the temperature of the space at each point. Because this is temperature function. Okay. Yeah. Well, high dimensional space, it's harder to understand the geometric picture there, and just because we cannot imagine for example, okay? So some phenomena you see, it's possible our universe just one slice in the high dimensional space. We don't measure the time. Time is artificial dimension, just a physical space. Our universe is the visible universe is three-dimensional space, but it's maybe embedded in the four high dimensional space. Okay, so some things some objects, for high dimension space, we cannot see it, but if I can project to a three-dimensional space, and you can see that this is how. Well, how do you imagine that? For example, take a picture of yourself, right? The picture is two-dimensional, right? I can still use a two-dimensional pictures to understand, even to make you. But you have to take a many picture around you. So go around you, right? And take a sequence of picture. And you look at your smartphone. Your smartphone has many smartphone has this feature called the 3D picture. So when you see some nice stuff, you can hold the camera and you go around this subject, and then you get a sequence of pictures. Actually, each time it's just like a movie. So each time you have one picture taken. So it's a projection of this 3D object on the two-dimensional plane. Okay, so you save this file just like you save a video. So when you see it, it's just a picture. Okay, but you can use a finger flip, and you can see that, the front side, back side, how does it look like? Okay, it's fun. I just discovered that when I was at time. Okay, so this is just sequence of picture. Okay, that's just the image. It's a three-dimensional object. You can use a sequence of a two-dimensional pictures to understand. Okay, but for four-dimensional object, imagine, how do you understand? If you're able to capture the picture of three-dimensional picture for this, and you get a sequence of three-dimensional object, okay, a sequence of three-dimensional images, and you can still talk about this four-dimensional object. Okay, so this is not a trivial science. Okay? So I stop here. I hope you can understand the multivariable calculus. Right?